All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 318, Electronic Circuit 1. Today is our 17th lecture, and by the Gantt chart here, well, of course, can you guys see it and also hear me? Yep. All right, thank you. So we are here. Here at this particular cell. Homework 3 is due today, and also by next Tuesday, what are we gonna do? You need to be aware of this. And next lecture on Tuesday, what are we going to do? Anyone is aware? Anyone knows what we're going to do? Here we go. Kevin is right. We're going to review. We're going to review because midterm 2 is coming. Midterm 2 is coming 1 week after next Tuesday. Okay. So be aware of this. So you can easily tell midterm 2 is going to cover whatever between the midterm 1 and the midterm 2, right? So it's module 3 and 4, chapter 3 and 4 as well. So it's all about the MOSFET, DC, AC, and concepts. Okay. So this is the our progress. And then before we step into more details in AC small signal analysis, let's review what we learned from last lecture. The most important thing is actually this small signal model of the transistor. Okay. Be very careful. We are talking about the small signal model of the transistor itself, nothing else. And the circuit, a complete circuit, contains transistor as well as different resistors, maybe capacitors, and other sources, right? So be aware of this, okay? So this is just a model of the transistor itself. Okay. In channel, we have GDS in this layout, and we are seeing VGS. We are seeing a dependent current source from drain towards source, so downwards. We also have an output resistor. And for P channel, the difference I'm emphasizing by the red color. Okay. So the VGS is not VGS. We are talking about VSG. This is the same thing happened in DC analysis too. Okay. And also the current of the dependent current source is reversed. It's from a source towards drain. And this is the same thing in the DC analysis. And the current value is GM times VSG. And of course, besides of these two models, we need to have two small signal parameters, small signal model parameters. One is output resistance. Another is the transconductance, if you remember the name, G sub M. They're respectively equal to VA divided by ID. Another is 2 times square root Kn times ID. So as I said, you want to print this particular page slide as one of your handout, okay, to be used during the exam, okay, because you really need it. And make sure that you're labeling the P channel on the same page, right, together with the N channel. You put them together. That's the easiest way for you to differentiate them. Okay. So these are the small signal model we learned, and based on which we go ahead to see how we're going to conduct the AC small signal analysis. Okay, which is this new PPT slides. Here, I'm directly providing the standard procedure. If you recall, we had something similar for DC analysis of MOSFET circuits. To AC small signal analysis, and never forget the first step is and always is DC analysis. The reason is same in the diode circuit analysis. We need DC analysis result for the AC small signal analysis. That's why DC goes first. Okay, DC goes first. Procedure has been instructed in previous lecture, so please go back to there to see. And then we are seeing the AC small signal analysis procedure. Okay. Basically, 1, 2, 3, 3 steps. First step, you need to calculate GM and R0, 2 parameters we just discussed under the dot count. And they both in terms of what? The DC analysis result, IDQ. So those two formula we just reviewed, and if you want more, once again, you print this page out as your handout. It's allowed to be used during the exam. Okay. This is the first step. You need parameters, GM and R0. Second step is find a circuit. Obviously, you need to find a circuit. This shouldn't be a big deal. However, you need to be very careful because afterwards the circuit analysis is based on this circuit. Okay, so how to find the small signal AC circuit? First of all, removing the DC source, short voltage source, open the current source. Here, of course, they all refer to the independent source. Okay. We shouldn't have dependent DC source in the circuit. We shouldn't. Okay. However, in terms of the concept, you need to be clear. We are eliminating those independent sources. Okay. Dependent sources we cannot touch. Remember that is 1 or 2 questions, multiple choice back in the midterm 1. Okay. Some memory there. Removing the DC source and then short all of the capacitors. Here, okay, we have 2 types of capacitors we could possibly come across. First one is called coupling capacitor. We discussed this already. Is input or output. And we have coupling capacitor series with input source or series with output. Okay. It's trying to coupling off the DC. Okay, only leave the AC pass through. It's a coupling capacitor. We have also second type of capacitor. We will see what does it look like and where is it. Okay. High pass capacitor. And we will see in the more specific circuit. And we will see it. Okay. How to deal with it. How to deal with it? Well, short. Okay, no matter which type of capacitor, we need to short it. We need to short it in 318 at least, because in 358 we need to consider it as an impedance, a frequency-dependent impedance. But here we just simply short it. Okay. And then what do? Start to place the MOSFET small signal model right in the middle of your paper. Be very careful it's N channel or P channel. And we just have reviewed the basic models for both. And also available in the handout I suggested you to print out. And then you connect, or say extending the circuit terminal by terminal. Okay, remember this rule. Terminal by terminal. You are not jumping. Okay, you're finish one terminal and then go ahead to next terminal. Okay, otherwise, it's going to be messed up. So I call it connect the resistors and this is source based on the given circuit. You're extending the circuit based on the given circuit. It's not randomly doing it, nor memorizing any circuit. Useless. Okay, don't memorize. It's all depending on the particularly given circuit. Based on that, you extending your small signal circuit. Okay? Don't try to memorize it. It doesn't work because the circuit variation is plenty. So could come across any kind of circuit. The third step is to find a gain. Circuit analysis, of course, circuit analysis. Here I'm providing, just like in the DC analysis, I'm providing an arsenal. Yeah, this arsenal is actually enough for you to queue any enemies, to queue any enemies, or say, take care of any circuits, if you consider that as enemy. What do we have? First, we can have output equation by Ohm's law. Second, we can have a input equation. What does it mean, an input equation? You're trying to link the input Vs with the VGS or VSG. It's a relationship between the Vs and the VSG. Either use a voltage divider or use a KVL loop. Okay. Either way, you can find a relationship, or say an equation, in terms of both Vs and the VGS or VSG. Okay. This is what I said, trying to link the input source Vs and the VGS. Third equation is the VGS equation. You might need this. Okay. VGS equation means VGS equals to what? VG minus Vs. Okay. Very simple. This equation means nothing but VGS VG minus Vs. Simply like this. This sounds like something we can hardly imagine how to use, but when you see the problem, and we probably can understand this better. Okay, this might be useful. It might be useful. And also remember to check what? To check the number of equations and the number of unknowns. It should satisfy this relationship. The number of equations is one less than that of unknowns. Therefore, you're not able to find, once again, you are not able to find the V naught individually. Can't find the input individually either. You can only find the gain between them, between two unknowns. Okay. So finally, you're looking for the gain, a ratio, per se, a ratio between two unknowns, V naught and the Vs. So if you're looking for the V naught equals to something, or you somehow obtain the V naught value, well, unfortunately, you're wrong. That's not possible. Except I specify one particular input for you, and I'm not planning to do that. Because the only thing matter to us is the gain. We don't need to worry about any particular output, at least not in this class. Any questions? Is this procedure sounds make sense, or any concerns?
Yeah, just to clarify with the lecture slides, are those part of the equation sheet, or can we have a separate equation sheet with that?
You mean during the exam, right?
Yes.
During exam, you are allowed to have one formula sheet, letter size, both sides.
Okay, so it is part of it.
And besides of that, let me finish. And besides of that, you can have the handout. And what handout is permitted? For example, this AC, this page, this one allowed handout. Another handout allowed is the page 6 in previous PPT. Third handout allowed is DC analysis procedure. For now, I can come up with these 3 handouts allowed during the exam, besides of the one-page formula sheet.
Okay, thank you.
Yep, sure. Any other questions? All right, if this is fine, then let's just try to apply these. Okay, apply this to our circuit, specific circuit. Well, here I'm receiving a question from Shane. Would you be able to send us the allowed handout so that we don't use something we are now supposed to do? I can send you a list, but obviously you still need to print them out yourself. I can list, by list, I mean I can send you a list saying this lecture slides, PPT, page number on it. I can send you a list. So that you know what to use. Well, of course, remind me once again by maybe next Thursday will be great. Okay, next Thursday, which means right before the midterm 2, right? Remind me that, and then I can send you a list. Okay. All right, sure. All right, so let's see how we apply the provided procedure on specific circuits, specific circuit. So first of all, let's take a look at this given circuit. Okay. No hurry. Okay, no hurry to jump into the circuit analysis. Okay. We want to go step by step. First of all, let's identify: is the N channel or P channel? N channel. That's right. 2 is right. First of all, you realize this is N channel, and also realize what? Drain here, right? Source down here, right? Gate here. Also, let's identify this common what and why. This common what circuit?
Common source.
The common source. Why is that, Josh?
The gate is the input and the drain is the output, so that means the source is not used, therefore it is common.
Very good. Everybody is following. So, as Josh said, the input of AC, once again, is AC input. It's going into the gate. It's occupying the gate terminal. And output, we just said, is here, is that drain, right? The output is labeled here. So we're talking about output here. Leaving the common terminal source as the common terminal for both input and output. Therefore, it's common source, and therefore it's common source. Okay, good. Okay, I see Kevin and Shane got it too. Good. So at the beginning, it's helpful to identify these 3 things, right? What 3 things? Terminals, channel, and common circuit, right? Identify 3 terminals, which is which, identify is N channel or P channel, and then identify the common circuit. Okay, these are helpful. And besides, it might be asked as one of the questions in the exam. Okay, be very careful, read carefully. All right, go ahead. Let's first of all try to obtain the small signal circuit. I think I give you guys 3 minutes to try this small signal circuit, just a circuit, okay? And then I present the solution, and then we will discuss from there. Okay, 3 minutes. Go ahead, try this small signal circuit. How to find it? Go ahead. All right, this is the solution for small signal circuit. Okay, you're removing the top DC source and keep the AC source here, and then place the N-channel MOSFET small signal model right in the middle. And so this red box here is the, sorry. This red box here is the N-channel MOSFET basic model. And then you're extending the terminal by terminal, right? First, you see the source here is what? The ground. The source is ground. Easiest one. And then you can go ahead to extending the gate. How to extending the gate? You see the gate is connected to what? R1 and R2, right? Then why R1 and R2 are parallel? Why is that? Because R2 is between gate here and where? Ground. Okay. This is R2. How about R1? R1 is between the gate and, because here, remember, we eliminate the DC source to ground. Okay. So R1 is also between the gate and the ground. That's why R1 and R2 are parallel. And after they're parallel, the gate is also connected to a shorted CC1 and RS, right? The gate connect to RSI. And then connect to the VI. And the other terminal, negative terminal of the VI is nothing but the ground. Here we go. Any questions regarding this extension of the gate, particularly just the gate? Source, I think, is fairly easy. How about gate? Does everything make sense? Good. Any other questions? Anyone? All right, if this is fine, then go to the drain. Drain, as you see, one is output, okay? Drain is output, so you gave output here. Drain also connect to RD, okay? And the other terminal of RD is what? Once again, ground. So drain connect to RD. The other terminal of RD is the ground. Okay, this is how we end up with this circuit. Take a look again to see any questions. Any questions anywhere need to be explained? Anything? All right, if this is fine, then now is the time for us to write equations. Right? Write equations. I know nothing is specified. We just use the symbols. The symbols R1, R2, etc., etc. Okay. So to do that, maybe we want to go back here and take a look. Let's see the first weapon in the arsenal. What is called? Output equation based on Ohm's law. Let's see what does it mean. Output equation is talking about output. How to write the Ohm's law? Actually, we did it last lecture already. What's the voltage here? This voltage just equals to, how about the current times the resistance? We have two resistors parallel, R0 and RD. They're parallel, right? So if you use this parallel total resistor as the resistor, we are looking for then the total current, which is where? Is this current. Does it make sense? This current here, I'm using red to label it, is equal to total current flows through R0 and RD. And of course, be very careful. The current direction in this way, meaning the current flow through R0 and RD are upward. Therefore, introducing a voltage with such polarity opposite to the V0. So what we need? A negative sign in the front. Right? That's why we have this equation, output equation, Ohm's law. A current times parallel between two resistors. And as I said, this voltage has the opposite polarity. So we give a negative sign in the front. Ohm's law output equation. Any questions? All right, if this is fine, then go back to our Arsenal once again. The second is the weapon is trying to link the input source VS and VGS. We call it the input equation. Okay. How to link these two? Well, input source is here. VGS is here. What's the relationship between these two? Anyone has any idea? How to link these two? Anyone? Any idea? Very good. Kevin is suggesting a voltage divider. So obviously, voltage divider means R1 parallel with R2 is sharing the total VI with whom? RSI, right? So these two are series connected and sharing the total voltage VI. And the VGS is nothing but the voltage across the R1 parallel with R2. Therefore, what is it? VGS equals what? Equals to the total voltage VI times voltage divider. And here, I think I forgot to specify, Ri here is nothing but R1 parallel with R2. Okay. Ri is nothing but R1 parallel with R2. Nothing but that. Okay. So this equation is the so-called input equation, linking the VGS with the input source. So now we have two equations. We can start to count. Okay, we start to count. How many unknowns? Two equations. How many unknowns now? Of course, we are assuming all of the resistance as known, as something given. We're not assuming them as knowns. How many unknowns? 3 unknowns, right? What are they? V0, VGS, and VI. 3 unknowns. 2 equations. What we need to do next? What we need to do? Calculate the gain. Exactly. Yeah, start to go for the gain. Why is that? Because we go back to the arsenal again. Okay. Well, of course, we are not using the third weapon, but the fourth weapon is telling us if the number of equations is 1 less than that of the unknowns, guess what? We should start to conduct algebra to find the gain. Now, it is the case. It is the case. Of course. Okay, don't take me wrong. Of course, number of equations, number of unknowns are perfect. However, you need to be careful. Are you having V0 and Vi as 2 of your unknowns? Okay, you need to have them. Otherwise, we can't find a gain. Does it make sense? Okay. You're probably gonna have like a Vx, a Vy somewhere in the circuit, but they're not VI, but they're not inputs or not the output voltage. And then of course, then you still need to have more equations because you don't have output voltage and the input voltage in your equations. You can't find the ratio between them, therefore. Okay, so you need to have them both in the equations as unknowns, and then you count how many unknowns, how many equations. Did I make myself clear here? You understand what I'm talking about? You must have these two. Does it make sense? All right, thanks. So how to conduct this algebra? Anyone can give a rough idea. How to conduct this algebra? Once again, assuming all of the resistance are given. How to conduct this algebra to find the gain. And of course, here I'm presenting the solution here, but the solution doesn't matter. Okay. Once again, don't try to memorize this solution. The solution is right, but it's useless. Don't try to memorize it. It's useless. Just how to conduct this algebra. V naught over Vi, correct. But how to conduct this algebra? Put equation for V naught over Vi, equation for V naught over equation for Vi. And that's basically right, but be careful. We're making them both V naught and Vi equation are in terms of the same variable VGS. And then if you do a ratio between them, you need to make sure the VGS can be canceled out. Because sometimes you cannot guarantee that. Therefore, simply looking for the ratio between V naught and Vi probably doesn't work. Okay, probably doesn't work. Let me explain this way. You have V naught in terms of, say, VGS times something. Constant maybe. If your Vi equals to VGS times something, and this something and this something are all in terms of resistance, means constant, and then yes, then you can do a ratio directly because VGS can be canceled that way, right? VGS is canceled, and you can receive the constant result. However, what if something you have like this? Here it's constant, maybe 100. You do the ratio here. Guess what? It's useless, right? Does it make sense mathematically? You do this ratio, no, it doesn't work 100%. It doesn't work 100%. So what I want to do is to remember. Once you got some equations, you want to try to derive VGS equals to what? From maybe equation 1. Okay, we call this 1, 2. Equation 1 derive VGS in terms something. And then substitute VGS into equation 2. In such way, you're able to what? Eliminate the VGS. This is a basic algebra. I believe all of you guys know how to do it, but the idea you need to keep in mind. You substitute the VGS. Okay? You derive the VGS from one equation and substitute the VGS into another equation. Then the VGS can be gone. Only V naught and the Vi left in the equation. And then you can, from there, to find the ratio between. This is how you conduct this algebra. Just remind a little bit. Okay. And then here we go. And that is the result. That's the result. Of course, in this particular example you're seeing, if you derive VI, it's also in terms of constant times of VGS, right? So is V naught, right? The constant times of VGS. Therefore, you do a division between two. Okay? Excuse me. VGS is canceled. End up with a constant. Good. This is easy. Any questions? And of course, here, this particular problem is emphasizing that the R1 and R2 are essentially parallel, because the other terminal of R1 up here is also ground in AC. Any other questions? All right, if this is fine, then we can move on. We can once again do the 3 identifications and then leave the rest of the job to you guys as exercise. So first of all, let's see, N channel or P channel? P. Yeah. Good. Very good. You guys identifying it. P channel. And also, source is up here, right? Drain down here. Gate is here. Therefore, is common what? Yep, common as again. It's a common source. It's a common source again. Input is a gate. Output is a drain, and leaving the source as the common terminal. Yeah. So don't memorize it, guys. In the past, there were students trying to memorize. So the common terminal is the one going to the ground. No, it has nothing to do with that. Okay. Example here, the common terminal source is to what? Through a resistor and reach what? Reach to positive supply, a positive supply. Of course, in the AC is the ground, but it's not directly go to the ground either. So don't memorize in that way. Memorize the rule. Identify the input, identify the output. The left one is the common terminal. All right, after these identifications, I give you guys, how about 10 minutes? You guys got the circuit and then the equations. Okay, no algebra is needed. Okay, no algebra is needed. There's just a circuit and equations. All right, go ahead for 10 minutes. And here I'm presenting the solution for the circuit. Okay, so for the circuit only, so you can check and keep working on the equations. So 3 more minutes. All right, folks, here are the input and output equations, and therefore the resulted final gain. Any questions? Any? Take a look at these equations. Here I'm receiving a question from Kevin first. Where did the R0 go? Well, here you want to be careful. Actually, if you have R0 there, that's not wrong. However, you need to, in future, read the problem carefully. If the problem is requiring the R0 or not. Okay, what I'm saying is here. Let me show in the doc. We all know that R0 equals to this equation, right? But you also need to remember VA is very big. So in some scenarios or in some problems, VA is given as what? Infinity. Therefore, R0 is infinity as well. R0 is infinity means what? Open circuit, very good. Okay, very good. Open, okay. Therefore, in that scenario, R0 open circuit, which means gone. Here, yes, it is assuming the R0, or say VA is infinity. Yeah, it's assuming that scenario. No, well, here the R0 is generally speaking very big. It's not small. And also, if R naught is small, guess what? We can't neglect it, right? Because if R naught here is small, well, we're going to have a short circuit here. Yeah, you have it backwards. That's right. That's right. Okay, so without R naught, you have this result. And the key is obviously in terms of circuits, the key is what? The presence of RS. You can't miss it. And our RS further including is including RS in the circuit, and further affects the circuit analysis equation. So take a look at the equation here. I think the first output equation is fairly easy, right? It's just one current, and also here is going downwards, right? Going downwards. So positive, negative, introduce the voltage. So directly current times the resistance equals to voltage without negative sign in front. The output equation is fairly easy. How about the second equation? Any questions about the second equation? And also, anyone can tell what equation I'm writing or how I come up with this equation. Are there any questions? You might have different equation you can present. Let me judge. All right, here. Let me explain how we got the second equation. Well, actually, can anyone tell what the second equation is? What equation? Where I came up from?
I think you got it from the voltage across R1, R2 parallel, which is a combination of the VSG and that voltage across RS.
Or in other words, this basically Kevin is right. Okay, I received this equation from what? From this loop KVL. Does it make sense? And inside of this loop, I have three voltages, right? Three voltages. Who are they? The voltage across R1 and R2, which is what? VI. This is very easy. Second voltage is what? VSG. And of course, be careful this polarity. Third voltage is what? Is the voltage across RS. So the voltage across RS is a little bit tricky, right? So voltage across the RS is equals to what? Equals to Ohm's law. The current through RS times RS, right? But what is the current through RS? What is the current through RS? Anyone knows? Negative GM VSG, exactly. Or you can't say a negative because you can label. By negative, you're assuming downwards as the positive direction. But however, the current flows through RS is nothing but this current, right? There's no current here. Okay, why there's no current here? Why no current here? Why? Open circuit, exactly. Drew is right. Okay, this is the open circuit. It's literally open circuit. Open circuit, no current. So there's no current here. The current of RS is nothing but the current here. Therefore, force is upward. And according to the Ohm's law, introduced the voltage across RS is positive here, negative here. This voltage equals to GM VSG times RS. And if you write a KVL inside of this, well, what is it? Negative VI, right? Negative VSG, right? And then what? Negative GM VSG times RS. Which is nothing but this equation. Of course, here is equals 0. For same equation here. You see it? Same equation. Does it make sense? This is how you link the VI and VSG. Good, good, good. So from the circuit, you conduct the circuit analysis, and nothing is able to beyond those things we learned from 235. Okay, nothing can beyond that. All right. And then we can count here, but we have 2 equations, of course. How many unknowns? Once again, V naught, VI, and VSG, 3 unknowns. We're good to go. Find the ratio between. Fairly easy. Okay. We get the AC gain. You got AC gain. Any questions? All right, if it's fine, then we can move on. Okay. Of course, for this second circuit, the key is how to deal with the RS. First of all, you need to have it presented in the small signal circuit. Second, you need to know how to take care of this relationship, or say the input equation, how to take care of this input equation. And as to the R naught, once again, read the problem carefully. It's all depending on the given VA, early voltage. Okay, so all depending on the given. Okay, the given infinity VA, that means you don't have to involve the R naught in the circuit at all. Okay, it's open circuit. Okay. This is what we learned from this circuit. All right, move on to next. Still, we identify this. Okay, so N channel or P channel. Here we go. N channel. N channel. Good. The second, well, we can skip the identifying the terminal directly. It's common what? Common what? The common drain. Shane is right. Shane is right. Why is that common drain? Input given to the gate. Where's output? Output is at source, right? Output is source. Look at the arrow. Output is a source, leaving the drain as the common terminal, the common drain. Okay. I know it's half slides. It says so. I know. It says, well, I won't consider you're cheating, but the thing is, in the lecture we do want to learn. So as long as you can understand this and then being able to correctly identify during the exam, then you're good. Okay. Because in the exam, of course, I won't leave this there, right? Telling you is figure 1 is showing a common drain circuit. And then please identify this, what type of common circuit this is. Well, that's a little bit, no nice word, but that's not going to happen anyways. Okay, that's what. All right. This is identifications, and then all right. Once again, go ahead for the circuit. Go ahead for the circuit and the equations if time permits. Go ahead. And here I'm presenting the solution for the circuit. Now, what this time is involving the or not, well, I'm sorry about this. I mean, if you're not involving it, that's fine too. Okay. It's all, once again, depending on the given problem. Okay. I'm not specifying this detail in the lecture, but just please be aware. It's all depending on the particular problem. Read it carefully. According to the circuit, you go ahead for the equations. Okay, you can see what kind of equations you need. Input equations, output equations. Then you see if they're enough. Because it's possible that it's not enough. Okay, that's possible. Not enough, you need to figure out something else. All right, 3 more minutes. Go ahead. All right. This circuit translation is not a necessary step, but if we do this, and the resulted circuit analysis gonna become easier, a little bit easier. So you can take a look at this, and if you don't like this or you didn't do this step at all, that's absolutely fine. Okay, absolutely fine. But I'm doing a translation here. I'm translating this circuit to this one. I don't know if it makes sense. And so basically what I'm doing is flip this part over and down. Therefore, the drain is shorted with this ground here. The drain here, up here, is shorted with the ground here, or say the ground of the VI. Okay. This is what I did to so-called this translation. So the source and the drain, source and the gate, I'm drag them in a line, into a line. So there becomes along the same line, and they're aligned. Any questions regarding this circuit change? And if this is fine, then we can go ahead to write equation for this circuit. Okay. Well, of course, feel free to use this circuit to write the equations. No problem. No problem at all. Okay. This step is not necessary. And then from this circuit, I don't know what equations you guys end up with, but here's my input and output equation. The input and output equation. Be very careful, the source is VI. However, the top node here, I call it Vin, or actually VG, which makes more sense. Vin is nothing but VG, right? Does it make sense? Because this terminal is gate. Outputs regularly, the voltage equals to current times the parallel resistance, RS and R0. Output equation. Input equation, what I have. Vin equals to a voltage divider. And inside of this loop, you're able to get the VG, or say, which is the voltage across the R1 parallel with R2, the voltage divider. However, what's the problem? Can you see? Anyone can see the problem? Exactly. Need VGS. Well, not only VGS. By problem here, I mean two equations. But how many unknowns? 4 unknowns, right? V0, Vin, Vi, and the VGS. 2 equations, 4 unknowns. What does it mean? Plus, or say what we should do. Rewrite? No. Nothing is wrong. We are not gonna rewrite. Here we go. Kevin is right. We need another equation. We are not having enough equation yet. So what can we do? I like the idea from the Daniel. He's saying VGS KVL. So VGS KVL means the loop containing the VGS. Obviously, in fact, this loop, right? So how to write this KVL? Daniel, how to write this KVL? Read yours. Read yours, not type yours. I don't have it completely done yet. Okay. Okay. Can anyone write this KVL here? You're working something out. Okay. Anyone can do this? Or you have different idea. That's fine too.
You'd have a minus Vn,
Minus V in.
and then you would have a plus VGS, and then the
Then
V
what?
naught. I don't know the V naught, but I don't know if that's going to be plus or minus. Looks like it's a plus, equal to 0.
Correct equation. Correct equation. No, I think maybe Daniel is trying to figure out the third term here as well. Let me explain why it's positive V naught. The voltage here very easy. Is a positive here, negative here, V in. You guys know it. The voltage here is positive, negative here, VGS. However, the tricky thing is what's the voltage here, right? Doesn't matter the polarity, but the voltage here across the dependent current source. Of course, here, if you're using GM VGS, that's disaster. Okay. Because GM VGS here is the current value, not voltage value. You can't use current value to write a KVL. That's conceptual mistake. Does it make sense? So what's the voltage across this current source? Nothing but V naught. V naught is the voltage across R naught, voltage across RS, and also the voltage across this dependent current source. It's nothing but V naught. Right? This is a third equation. 4 unknowns, 3 equations, done. Right. Of course, here I'm using a little bit different idea. This is the equation, the same equation as this one. However, the idea is different. My idea is very straightforward. I'm not writing any KVL here. I'm just writing VG, which is V in, minus VS, because this is S, right? This is source. VG minus VS equals to VGS. VG is V in, VS is V naught. So V in minus V naught equals to VGS. This is the third weapon in the arsenal. If you recall back to here, the third weapon, VGS, a voltage difference between the gate and the source is VGS. It's a very plainly described the definition of the voltage potential. Right? And this is the third weapon in this circuit. Okay, VG is V in, VS is V naught. That's why V in minus V naught equals to VGS. Now we have 3 equations, 4 unknowns, done. All right, I think that's all for today, and thank you for attending today's lecture, and talk to you guys on Tuesday. Remember to review, review these things, otherwise you're gonna very easily forget them completely. Completely, very easy to forget them. So review them during the weekend, and see you guys next week. Bye now.